Hello and welcome. So an English teacher speaking to a student in class says, "Tony, name two pronouns." Tony, who suddenly wakes up, says, "Who? Me?" But you're not going to want to fall asleep in this video, because in this video we're finally going to prove those derivative shortcuts that we learned way back in Packet 5, starting with the power rule. So you'll recall that the power rule says that the derivative with respect to x of x to the n is n times x to the n minus 1. I hope at some point you asked yourself, why is that? I mean, how do we know that it's always true? These are questions that I encourage you to ask in all areas of your life, but they're especially important in mathematics. To answer these questions, we always need a good argument, something that will undeniably convince us that it's true. In other words, we need a proof that it's true. So how can we prove that the derivative of x to the n is equal to n times x to the n minus 1? Well, we can start with the definition of the derivative. And that's what's being done here. We're writing f prime of x, for f of x equal to x to the n at least, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That is the definition of what the derivative means, the limit definition as we've sometimes called it. But in this case, f of x is x to the n. That's the function that we're interested in. So we can plug x plus h into that x to the n function, and we get x plus h to the n. And we have minus f of x, which just copying that over is x to the n. And then all over h. Now, to take a next step, what we're going to have to do is expand out the x plus h to the n. And there's something that you learn in pre-calculus called the Binomial Theorem, or the binomial expansion, which allows us to do that. It gives us a way of expanding binomials, two-term polynomials, like this x plus h that has two terms. So it turns out that the expansion, if you remember the binomial theorem, is the first term raised to the n plus, and then this special notation is n choose 1, n choose 1. You might remember this being the second entry of a row of Pascal's triangle. And if that's not ringing a bell, that's not too big of a deal here. We're just going to be going over the power rule, and this particular one I won't ask you to prove on a quiz or a test. But it's good to know because we use the power rule all the time. We should definitely know why it's true. So for this n choose 1, that's the coefficient, the binomial coefficient of the second term of the binomial expansion. And then x goes down by a power, and then h, the second term, goes up by a power. Then you have n choose 2, x goes down a power, h goes up a power. And this keeps going on until you get to the last term of the expansion, which is this h to the power of n. Again, if you don't remember the binomial theorem, you can go back into pre-calculus and review it. But otherwise, we're going to move on. So we have minus x to the n all over h. Now you'll notice that you have an x to the n up in front, and then an x to the minus x to the n in the back. So those two will cancel, and you're just left with the middle terms. Now all of the middle terms have a factor of h, which is great because then we can cancel off that factor of h that we always want to cancel off, so that we can finish evaluating our limit. So every single one of these terms gets divided by h, and you end up with n times x to the n minus 1 for the first term. All the rest of the terms, because of their higher powers of h to begin with, now have h to some power attached to them, so that when we take the limit as h approaches 0, by plugging in h equals 0, all of these terms go to 0. So the only remaining term is the one that didn't have an h attached to it, which was the n times x to the n minus 1. And that is the power rule. That's the derivative of x to the n, is n times x to the n minus 1. So by taking these steps, by using that definition of the derivative, and some algebra steps, some knowledge from pre-calculus, we're able to figure out what the derivative of x to the n is in general. So that's great. Now we know why the power rule is the way it is, and we can prove that the power rule is true. We know that it's always true because we can always take these steps. Let's turn to some other functions like the trig functions. Before we figured out the derivatives of sine x and cosine x by the definition, we're going to need these two limits. The limit is theta approaches 0 of sine of theta over theta equals 1. Now that takes proof. There's an argument for that. There's a good geometric argument. We're not going to go through that here, but I hope that you're interested in wondering why that is. Why exactly is that? So you can check out the proof of that limit either in the textbook or you can search it up online. There are lots of geometric proofs out there, and I encourage you to go explore them. There's another limit that we're going to need, which is the limit as h approaches 0 of cosine of theta minus 1 all over theta, and it turns out that that's equal to 0 for that limit. Again, a geometric argument can be used to prove that. Now, once we have these limits proved using those geometric arguments, then we can find the derivatives of sine and cosine, sine x and cosine x, using these steps. So the derivative of sine of x is, by definition, the limit as h approaches 0 of f of x plus h minus f of x all over h, where f of x in this case is sine of x. So we have sine of x plus h minus sine of x all over h. Now sine of x plus h, really the only step you can take at that point is to expand out the sine using the addition identity for sine, which says that this expands to sine of x times cosine of h plus cosine of x times sine of h, and then you have the minus sine x that you can copy down. And then the next step we could take is factor out a sine x from the first term and the last term, and you'll be left with cosine h minus 1 from those two terms. Then the plus cosine x sine h we can copy down, and then what we can do is split this up into two separate fractions, one for the first term and one for the second term. Each of those would have an h underneath. And we're going to write it in this particular form: sine of x times cosine of h minus 1 over h, which we like because we know the limit as h approaches 0 of cosine of h minus 1 over h. That's going to turn into 0 based on what we said above, plus cosine of x times sine h over h, and that's great because the limit as h approaches 0 of sine h over h is going to be 1. So we take those individual limits, cosine h minus 1 over h, that goes to 0 as h approaches 0. Then sine of h over h goes to 1 as h approaches 0. The sine x and the cosine x, those ones are not going anywhere because all we're doing is moving the h variable to 0. We're not changing the x variable here. So you just have sine x times 0 plus cosine x times 1, which is cosine x. So the derivative of sine x is cosine x. You can do the same kind of thing for the derivative of cosine x. Use the definition of the derivative. So you'll have cosine x plus h minus cosine x all over h. Expand out the cosine of x plus h using the addition formula for cosine. Remember, the addition formula for cosine flips the sign, so if it's x plus h, you're going to have a minus between the cosine x cosine h and the sine x sine h. Then you can factor out a cosine x from the first and the last term, and that'll give you the cosine h minus 1 that you can put over h. And then you have this sine h that you can put over h as well, very similar to the derivative of sine x. And then the cosine h minus 1 over h goes to 0. The sine h over h goes to 1 as h approaches 0. And you get cosine x times 0 minus sine x times 1, which is negative sine x. So the derivative of cosine x is negative sine x. Now again, we didn't show the full proof because we haven't completely proved these two limits, the limit of sine theta over theta and the limit of cosine theta minus 1 over theta. We haven't actually proved those, but again, those are geometric arguments that can be made, and people have made them. So that's sine and cosine. What about tangent and the rest of the trig functions? Well, once you have sine and cosine under your belt, once we've proven those two derivatives, we can use those derivatives to help prove the derivative of, say, tangent x, which, recall that the derivative of tangent x is secant squared x. The way we can do that is by rewriting tangent x as sine over cosine. Sine x over cosine x. Now we can use the quotient rule because now we have the quotient of two functions, so we can use the quotient rule to help break down this derivative into simpler derivatives, in particular derivatives of sine x and cosine x, which we now know and have proven. So we're going to go through the quotient rule. Low d high. The d high, the derivative of sine x, we just proved was cosine x, minus high d low. Remember the d low, the derivative of cosine x, we just proved was negative sine x, over low squared. Great. Let's simplify on the top to get cosine squared x minus, plus sine squared x over cosine squared x. And now, if you notice cosine squared x over sine squared x, cosine squared x plus sine squared x, what does that equal to? If you said 1, that would be correct. So we have 1 over cosine squared x, which is secant squared x. Usually at the end of proofs, we celebrate with a little box. So we'll do that. Signals the end of the proof. So that's great. We were able to prove that the derivative of tangent x is equal to secant squared x by knowing the derivatives of sine x and cosine x, which we had just proved the moment before. So that's it for this video. In the next part, we're going to explore some derivatives of the other functions like exponentials and logarithms. Thanks for watching, and see you in the next video.